Welcome to a calculus video on integral applications. One of the most interesting yet challenging topics in integral applications is volumes. And we're just going to touch on a few basics in this video. Number one, square cross sections. Number two, circular cross sections or a solid of revolution. And the washer method. So let's take a look at those three situations right now, and then we'll jump into some not really examples, more just kind of trying to set up those ideas. And basically all three of these things have one thing in common. It's that we're just doing a slice method. We're just slicing the three-dimensional solid and looking inside it and see what it looks like. So the first one is a square cross-section, and usually just starts with a simple function, either a line or a parabola. So many examples just start out with that function, and they have kind of a confusing description on how you do that. Basically, they'll say something like the cross sections are perpendicular to the x-axis. So I just want to point out what that looks like. So if you have these two functions, let's call this this is just a line. So the question will say something like the cross sections are perpendicular to the x-axis. So if that's the case, we would sketch those like this. And basically, if you're looking at this from the right side, you see a square. It's basically a diamond from our perspective, but it really is a square because all of the sides are the same value. Now to make it a little bit easier to see, we'll sketch these other parts, and these are cross sections as well. Now you might not see it right away, but then if you say, oh, well, let's see what's behind, you could finish off the idea there. And you look at the textbook and it will show some of these visuals. The most common calculations we'll do with this square cross section is either the functions connect the diameter, in this case that's what's happening, or the function connects the sides. So it would be just kind of a normal square that is, I don't know how you describe it, it's just a normal square instead of diagonal. All right, then the unique ones show up in that you would get some sort of semicircle that's going on, such that this is the diameter and it's like a semicircle, half circle that goes around this side. That's a little bit more annoying. All right, so the basic setup here is just thinking about first, what's the area function? And here's a little shortcut. The area in this case is d squared over 2. And you could solve a triangle to figure that out. Basically you're solving 45, 45, 90 triangle. That's a little shortcut that you could use, and therefore the volume of all of these squares together is the integral function from a to b, so in this case maybe 0 to 10 or 0 to 12, whatever, of the area function that happens to be based on x. Okay, the next one is called a solid of revolution. It's specific to circles, meaning you're going to take a function and you're going to revolve it around the x-axis or the y-axis. So we first start with this function, some sort of complicated, it doesn't have to be that complicated. It could be a function that's raised to the third power. And the first thing we want to do is just reflect it over the x-axis. So it's a little bit tricky, which is why we learned this sort of stuff in previous classes. But that's a basic reflection, not the greatest. And so what I'll do next is I just want to connect either end of the function, so I could create this vase looking thing. And so I get the left side, and I'm kind of thinking about a pottery class that I took, and this is what it would look like if I was working on the pottery wheel. Now the key part of this step to understand any of these visuals is to draw a normal cross section of this situation. So it's this circle right here that helps us identify the fact that the radius of every circle is actually the function value. So radius equals f of x. Same idea goes if we're going to use dy, like if we're going to rotate around the y-axis, we would just have radius is equal to f of y, and we just have a y in our equation. So we think about the area of this cross section here, and the area is just pi r squared. So that would be pi times f of x squared. So whatever that function is, doesn't matter. that's going to be our radius. And if it's more complicated, it makes the situation more difficult. And then the volume of this entire shape, this face, is the integral from a to b, whatever that is, of the area function, which is just this result up here in terms of x. So this notation x and dx are saying the information, the function that you have in the integral is in terms of x. There are no y values. And then we just carry on from the fundamental theorem part 2 to find out what that volume is exactly. And anytime there is just some basic values or something that we could do, like we'll do that by hand, analytical. And then the result will be in terms of units cubed, whatever units those are, which we don't care too much about at this point. All right, so those are the two methods. Here's the third method. So these two functions, a little bit different than the original visual I gave you. This one looks a little bit more like parabolic in nature, not exactly curved there. But basically these two functions I just pulled out of an example from the textbook. And what's going on here? The top curve is a cosine curve and the bottom curve is a sine curve. And the question situation says something like, we have this area that's in between cosine and sine. It's bounded between those two. It doesn't say when sine and cosine meet, but we could think about it briefly and realize that it's pi over 4. And find the volume of the solid generated by revolving over the x-axis. So this is kind of like the solid of revolution, but it's a little bit more intense. It creates a washer cross-section, which ultimately looks like a donut. And it's the shaded region where the sprinkles are. All right, so the first thing we'll do is similar to the last thing, is we'll reflect this sine curve over the x-axis, reflect the cosine curve, you know, best of our ability, and then we'll do the cross sections again. So sometimes this gets a little bit harder to do the cross sections, and on the far right here in this particular case, it's just open. But the key spot is this center cross section. So I'm going to make it nice and wide so that you can see it. So then the inner piece of the donut, which is empty, is inside the yellow spot. So here's the yellow where the donut is. And then the red as the outer piece. So what's happening is, like, on the far left, the donut is wider. In fact, it's completely sealed. This is kind of like a dog bowl that could sit sideways on the floor. So right now you were seeing it as sideways. And then the donuts are getting thinner and thinner and thinner as we come to the right here. Okay, so what is the area for this? Well, the area is, well, let's see here. This is pi r squared. I used a big R because that's the bigger piece of the donut. And then minus, I'll do the yellow, pi little r squared. Okay, not too bad. The most common mistake that students make is they'll do pi r minus r squared. Like they'll subtract the r's first and then square that. And we know that that's not the same thing. So then the volume is the integral from a to b of pi big R squared minus pi little r squared dx or dr. So I'm going to stop there. There are definitely plenty of examples that could be worked out, but at this point, students who have studied areas between curves and the fundamental theorem of calculus can apply these concepts to the questions and get some visuals set up and find the volumes. My next video will have specific homework questions set up so you could see what the wording is and how to break down the wording into an actual visual that you can then create an integral for. So check out that one.